All right, so in qualitative analysis, it's not a really difficult topic, right? So what we are trying to do is identify particular sets of ions using specific reagents. All right, so we will have specific sets of cations that you will have to know, as well as specific anions that we will also have to know. So the cations that we will look at is let me just put them on the board. So we have specific cations that we will identify. And these cations so these cations we have Fe2 plus, Fe3 plus, 2 plus. These ions are the easiest one. The reason for that, they formed colored solutions. So Fe2 plus, if Fe2 plus is present in a solution, that solution will appear green. If it's Fe3 plus, it will have a red-brown color. And if it's copper 2 plus, it will have a blue color, right? So if you are testing for any cation, right, and you get a green color, you know it's Fe2 plus. Blue color, that's copper 2. So once you see these colors, they tell you which ion is present. All right, just a second. No, there are some other ions. Sorry, I'm just adding some people here. All right, no, these are easy. They have distinct colors. But for Mg2 plus, Al3 plus, Ca2 plus, Zn2 plus, and Pb2 plus. All of these ions here, they will give you, in solution, you will get a white precipitate. So these ions will not give you a distinct color. So unlike these three up here, these ions here, they will not give you a distinct color. No. So once you add them to the solution, and now the solutions we are going to talk about are sodium hydroxide and ammonia. So before I show you how to use them, just know the color change. So Fe2 plus is green, Fe3 plus red brown, Cu2 plus is blue. Then these 5 ions here, all of them, the only color you will get is a white precipitate. All right, so just make a note, and then I show you how to proceed.
Yes, sir.
Is anybody writing, or I can erase the board?
I'll finish,
I'm
right?
finished, sir.
All right.
Definitely.
So the first part of the class, we are focusing on the cations, because we will also have to identify anions as well. All right, so we are going to start off with the sodium hydroxide solution. So when we want to identify our cations, we use two solutions, sodium hydroxide solution and aqueous ammonia. For those of you who do biology, right? If you want to test a food sample, if it has in starch, we normally add iodine solution, and we should expect a blue-black color. So if you add iodine solution to a food sample, right? And let's say you get a green color, would that indicate that iodine is present?
No, sir.
Exactly. So it's the same thing we are going to be doing here. We're going to add sodium hydroxide, and based on the observation, we will know which ion is present. So what we're going to do with the sodium hydroxide, we're going to add it dropwise, right? So just a few drops, and then we are going to add it in excess. So what happens if we add it dropwise? So if you add it dropwise, and you get a green precipitate, we already know that which ion would give us a green precipitate.
Iron 2.
That is correct. PPT is precipitate for short. So if you get a green precipitate, that means Fe2 plus is present. If you get a red-brown precipitate, which ion is present?
Fe3 plus.
That is correct. All right, so Fe3 plus. And if you get a blue precipitate, which ion is present?
Copper. Copper 2 plus.
That is correct. So if you add sodium hydroxide dropwise, and you get a colored precipitate. So no, these are the colors. No. Is someone asking a question? All right. So other than these three ions, what you might get next is a white precipitate. Now, if you get a white precipitate, the following ions may be present. Please repeat. There's someone talking. I can mute. I'm not hearing it. If you have a, you can text it because I'm not hearing it well. Someone's mic is on. All right, look. Give me a second. Sean, Ashley, Sean and Ashley, can mute my call. Let me just mute Ashley. All right. All right. If we get a white precipitate, which ions may be present?
Magnesium 2 plus, aluminum 3 plus, and lead 2 plus, zinc 2 plus, and calcium 2 plus.
right? So if you get a white precipitate, when you add sodium hydroxide, dropwise, magnesium, aluminum, calcium, zinc, and lead may be present. So this would be the starting point. So the most important part is the white precipitate, because once you get a color, you know which ion is already present. But if it's a white precipitate, you have to choose between 5 ions. So what we're going to do now is focus on the white precipitate. When we add this sodium hydroxide in excess, all right, these ions, so the Fe2 plus, Fe3 plus, and Cu2 plus, all of them are insoluble in excess sodium hydroxide, so they will not dissolve. So when you add a few drops of NaOH, you will get a precipitate. If you add a lot of NaOH, lot of NaOH, the precipitate that is produced, it will not dissolve in the excess. All right? Now, on the exam, you might be asked to write an equation. So when you react the Fe2 plus with sodium hydroxide, what is happening is that the Fe2 plus ions react with the hydroxide ion to produce iron 2 hydroxide, which is insoluble. And so your state symbol here, it should be a solid. And so this is what happens for each of these.
Sorry, I forgot.
Yes. Thanks for that. Right, so what is happening? Each ion is combining with the hydroxide ion. So if it was Fe3 plus, what would have been the equation if it was Fe3 plus? What would we use?
Fe3 plus 3.
So Fe3 plus, always put your state symbol
Plus 3
hydrogen,
OH negative.
right? And that would produce
Fe open bracket OH close bracket 3.
that is correct. Solid, right? So if you're asked to write an equation, that is how you would do it. The positive ions are combining with the negative hydroxide ions, right? So the same thing would happen for copper 2 as well, right? So you can just make a note of the equation, and also that when we add it in excess, iron 2, iron 3, and copper 2, they will not dissolve in excess sodium hydroxide. Once you're ready with that, we will move on to focus again on the white precipitate. So everyone has the equation now? Anybody writing?
Yes, sir. Yes, sir. Hold on.
All right.
Yes, sir.
I can erase this side now.
No,
Yes,
sir.
sir.
Alright.
No.
Oh, sorry. You have to write up this? What was up top? I
Yes.
have it.
Yes, sir.
You can write it back, please.
Alright. Alright, so for those that are just coming in, the class is being recorded and you will get to view it after if needs be. Alright, let's, somebody's mic is on. Let me check.
Sir,
Yes,
for this test, you're testing for iron.
no, I'm just telling you what will happen based so for the testing. I'm just telling you how we identify each of the cations. So we look at when you add the sodium hydroxide dropwise, if you get green precipitate, that indicates Fe2 plus, red brown indicates Fe3 plus, blue indicates Cu2 plus. If you get a white precipitate, it can be magnesium, aluminum, calcium, zinc, or lead. Now the question for the inference section, you might be asked to write an equation. And the equation is an ionic equation. So what is happening is that the ion, any of these cations here, even though you're reacting it with sodium hydroxide, the cation is combining with the hydroxide ion. So this would be your ionic equation. Any of the cations with the hydroxide ions. So if you're asked to write an ionic equation or just equation, this is how you will do it. The cation with the hydroxide ion. Right? So let's now move on to the white precipitate. Now, some of these will dissolve in excess, sodium hydroxide, and some will not. So for magnesium and calcium, magnesium and calcium, these two ions will not dissolve when you add this sodium hydroxide in excess. But for calcium, sorry, not calcium, for lead, zinc, and aluminum, these three are soluble. So in the first part, right, let's say we add this sodium hydroxide dropwise and we get a white precipitate. It means that any of the 5 ions can be present. However, when you add it in excess, if the precipitate dissolves, then one of these 3 ions are present, right? If it does not dissolve, then one of these 2 ions are present. So all you need to do is remember this information. So when you get the test, as in the exam, based on the observation or the inference, so if you get the observation, you should know the inference. And if you get the inference, you should know what the observation is, right? So if we add it in excess and the precipitate does not dissolve, one of these two ions may be present. However, if it dissolves, one of these three ions may be present. Now, this is as far as we can go with sodium hydroxide, right? So we cannot go any further than this. So using sodium hydroxide, the most we will be able to say is that magnesium or calcium is present if the precipitate does not dissolve. And if it dissolves, the most we can say is that lead, zinc, or aluminum may be present. So once we have done this part now, we would have done a further test using aqueous ammonia. So the first reagent to start with is sodium hydroxide. And then we're going to use aqueous ammonia to narrow it down some more. All right, so that is what we're going to do next. So as soon as you're finished, you can let me know and we will move on to aqueous ammonia solution. Finished. All right. Is anybody writing? Yes. All right, good.
Sir, I'm screenshotting the information.
All right, no problem. No, we will do this same thing for the aqueous ammonia. I came late, so where could I get the recording? I'm going to post it to my YouTube channel. I will give you the name of it shortly.
When see your boy have a girl in my lap, in my hand now.
Somebody's mic is on.
You know, sure. This one.
Right, so just like how we add the sodium hydroxide dropwise and then in excess, we're going to do the same thing for the ammonia. Now, when you add the aqueous ammonia, the observations for the Fe2 plus, Fe3 plus, and Cu2 plus is going to be the same. So you will get your green precipitate, red-brown precipitate, and your blue precipitate. These ions, you will all get a white precipitate except for calcium. Right? So calcium, it will not give a white precipitate with ammonia. So let us say, right, that we add this sodium hydroxide dropwise and we get a white precipitate. We add it in excess and it does not dissolve, right? It means it is magnesium or calcium. Then we use the ammonia solution now on this solution. If we add the ammonia and we don't get a precipitate, then we know that it is calcium, right? If we get a precipitate that does not dissolve in the ammonia, it's magnesium. So this is how we're going to use ammonia solution to narrow down and identify our cation. So calcium, it does not form a precipitate with ammonia any at all. So that's the first point you should note. Calcium does not form a precipitate with ammonia. So you will just get a solution. There will not be any precipitate in it, and that is for calcium. So when you add ammonia dropwise, if you get a white precipitate, will be magnesium, aluminum, zinc, or lead. All right? Calcium does not form a precipitate with ammonia. So once we add it dropwise, we are going to go ahead and add it in excess. When you add it in excess, if it does not dissolve, the ions present may be magnesium, aluminum, and lead. And if it is soluble, it is zinc. So remember, we're adding it dropwise first, and then we're going to add it in excess. When you add it dropwise, if you get a white precipitate, just take calcium out of it. All right? It's either magnesium, aluminum, zinc, or lead. When you add it in excess, if you get a white precipitate, it may be magnesium, aluminum, or zinc, or lead. But if it is soluble, it is zinc. All right? Now remember, just a second. Now remember, let me just add these people. Remember that magnesium, yes, go ahead. Remember that magnesium, we would have already differentiated it from aluminum and lead when we use sodium hydroxide. Because remember, aluminum and lead would have been soluble in sodium hydroxide, in excess sodium hydroxide. But magnesium would not have been, because magnesium is insoluble in excess sodium hydroxide. So when you come and use ammonia now, if you get a white precipitate again that is insoluble, right, with the ammonia, you can ignore magnesium and focus. Just a second. You can ignore magnesium, right? Because we would have already figured out if it was magnesium versus aluminum and zinc. So let us work on the notion that the white precipitate, it is soluble in excess ammonia. Sorry, in excess sodium hydroxide. So that would have been 3 ions, aluminum, zinc, and lead. So if we are using ammonia now, and you get a white precipitate that is insoluble in excess ammonia, then we know it would be aluminum or lead. So what is going to happen next now is to confirm whether you have aluminum or lead. And to confirm that, we're going to use a solution containing iodide ions. All right? So you can use potassium iodide or sodium iodide. And what is going to happen is that the lead ions are going to combine with the iodide ions to give you a yellow precipitate of lead iodide. So let me see if I can do this. So Pb 2 plus, let me just erase up here. So to confirm the presence of lead, right, I'm just adding someone here. To confirm the presence of lead, we use the potassium iodide or sodium iodide. So the lead ions will combine with the iodide ions to give you a yellow precipitate of lead iodide. And it is insoluble, hence I have this solid here. And to balance the equation, I will pick up 2 in front of the iodide ion. And that is it for the positive ions. So let's
So,
just recap. Hold on, okay, go ahead and answer the question.
so when I say insoluble, I mean like it does have a white color,
Right.
aluminum and
So,
lead.
so yeah, you would see a white solid form. So remember, precipitate means solid. So when you get the white solid, if you add the sodium hydroxide in excess, and then it just turns into it gets colorless. So if the precipitate dissolves, the solution is going to become colorless, right? So you will actually see that happen. So you add a few drops of ammonia or NaOH, and you just see white solids appear. So let us say that this is the test tube, right? And you have this solution of your cation, and you add a few drops of ammonia, you will just see solids appear in it, which we call our precipitate. All right, so that's what happens. You add your solution, right?
Sir,
Yes,
so it would be like a white cloudy look.
yes. And there's a link where when I give you the name of the channel, you just go on the CSEC playlist, click CSEC Labs, because I did the video for this, the actual experiment, and upload, so you can actually see it for yourself.
So when you finish, you can send the link in the chat.
All right, sure.
Yeah.
Sir. Sir, so you say when it shows the white precipitate is insoluble.
Please repeat.
Huh?
Please repeat your question.
When it shows the white precipitate is insoluble.
No, so there are two things we do. We add the dropwise, and then we pour out a lot of sodium hydroxide. So when you add it dropwise, if you get a white precipitate, it's an indication of the fine ions. When you add a lot of it, so the precipitate is a solid, right? So you add a few drops and you will see a solid appear. So when you pour out more of the sodium hydroxide or the aqueous ammonia, if that white solid dissolves, then it is soluble. But if it does not dissolve, then it is insoluble. So
So when I say dissolved, I mean like it clear.
yes, right. So just like if you're mixed drinks, right? Or if you're mixing tea and you throw the sugar in the cup, just a second. If you pour salt or sugar in water and mix it, you expect it to dissolve, right?
Yes, sir.
Right. And then once it dissolves, that's what we say it is soluble. So sugar and salt, those are soluble in water, because if you add it, it will dissolve in the water. So for sodium hydroxide, if you just add a little bit to a solution of a particular cation, let's say you don't know which cation it is. So you just add a few drops of the sodium hydroxide and the white solid appears. It tells you that the formation of that white solid, it tells you that it could be calcium, it could be lead, magnesium, aluminum, or zinc. So in qualitative analysis, we're trying to identify either cations or anions. So remember, a salt is made up of what? A positive ion and a negative ion. So you dissolve this salt to get a solution. And then we add sodium hydroxide and ammonia to figure out which cation is present. If you get a white solid forming when you add a few drops, that white solid, it can be magnesium, aluminum, calcium, zinc, or lead. but we need to figure out which one of it, which one of these ions is present. So we can't work off one of these 5 ions may be present. We need to know which one of it is present. So what we can do after we add the dropwise is to add it in excess. And in excess means you pour out a good amount. So when you pour out a good amount, if it dissolves, not all of these will dissolve. So not all of them are soluble. Some are soluble and some are insoluble, right?
Insoluble, insoluble, soluble in sodium hydroxide or in NH.
All right. So let me just recap. So for sodium hydroxide, if we're doing sodium hydroxide, magnesium and calcium, those are the ones that are insoluble. So if we were using sodium hydroxide solution and we add it in excess, magnesium and calcium, those are the ones that are insoluble. So if you get the white precipitate initially, and when you add more sodium hydroxide, the white solid is still present, then that white solid is either magnesium or calcium. However, if the white solid dissolves, right? So the solution it gets clear again. Then the ions, the possible ions are zinc, zinc, aluminum, or lead. So what you need to remember is that zinc, aluminum, and lead, they are soluble in excess sodium hydroxide. Meaning, once you add sodium hydroxide in excess, the white precipitate that is going to be formed, it will dissolve. Magnesium and calcium, they are insoluble. That means it doesn't matter how much sodium hydroxide you are adding, the white precipitate is going to remain. It will not disappear. It is going to stay. All right? So if you are trying to figure out, if I give you a solution, right, a colorless solution, because remember, if it is colored, you can figure out which ion it is right away. But if I give you a colorless solution, you start with sodium hydroxide. What is going to happen? You add it dropwise, and you get a white precipitate, indicating one of 5 ions. Then you pour more of the sodium hydroxide. One of 2 things are going to happen. Either the precipitate stays or it dissolves. Right? So one of 2 things will happen. Either the solid dissolves. So when it dissolves, if it dissolves, we say it is soluble. If it does not dissolve, we say it is insoluble. So it's just one of 2 things can happen. It dissolves or it don't. If it dissolves, sorry, let me just add a few more persons. If it dissolves, then it's lead, zinc, or aluminum. But if it remains, it's magnesium or calcium. So your job is to remember this, information. So when you see a question based on the clues given, you will know what to do with the clues. So this is basically like a puzzle, right? We're just figuring out things based on the clues given, but you have to remember what happens in each case.
Sir,
Yes.
sir, you can go over ammonia part, sir.
Yeah, man. So sodium hydroxide at the end, sodium hydroxide will just let you know. Sodium hydroxide will just let you know if you have calcium or magnesium, or it can let you know, say it is lead, zinc, or aluminum. Now, when you shift from the sodium hydroxide to the ammonia, the ammonia now is going to narrow it down a little more. Just a second. Let me mute that first. Right. When you get to ammonia now, the first thing you are going to notice, when you add it dropwise, with the calcium, when you add it dropwise, if you don't get a white precipitate, calcium is present. Right? So you add ammonia dropwise, you don't get any form of precipitate, the calcium ion is present. So make a note. If you add ammonia dropwise and you don't get any precipitate, then calcium is present. However, if you get a white precipitate, then it's magnesium, aluminum, zinc, or lead. So that is the difference between.
Sir, so basically, you said the calcium, the calcium soluble in the ammonia.
That is correct.
Oh, so the
Right.
type number this would have to change then. Correct me, I look for it.
Right, yeah, here it will change.
Okay.
Right. So dropwise, if you don't get any precipitate with ammonia, it's calcium. All right. Now, if it is insoluble, it's lead, aluminum, or magnesium. So if you get a white precipitate that is insoluble in ammonia, lead, aluminum, or magnesium is present. Now, if it is soluble, the only one that is soluble in ammonia is zinc. So after we use sodium hydroxide and we move to ammonia, we can figure out a little more if zinc is present or lead and aluminum. Let me tell you why. If after you use sodium hydroxide, right, you get a precipitate that does not dissolve in excess, it's either calcium or magnesium, because those are the only two that are insoluble in sodium hydroxide. So if after you figure out that it's either calcium or magnesium, right? And then you come to ammonia. If you add the ammonia and you don't get a precipitate, then it simply means that magnesium is present, calcium is present. But if you add the ammonia and you get a precipitate, then it's magnesium, right? Now, if you add it, let me just add this first one. If you, at the end of the sodium hydroxide reaction, we determined that it was lead, zinc, or aluminum. When we get to this state with ammonia, if you get a white precipitate that does not dissolve in excess, it is going to be lead or aluminum. And if it dissolves, then it is going to be zinc. So once you get to this point, that is where we stop with ammonia.
Yeah, so why not put calcium too on the soluble part?
Oh,
Yeah.
I had pointed out calcium earlier, but yes, zinc or calcium. So what is going to happen? This is as far as you can get with ammonia. So to confirm lead, so remember now, you will be trying to differentiate between lead and aluminum. If magnesium was present, you would have figured it out because magnesium is insoluble in both sodium hydroxide and ammonia. That is the only ion that is insoluble in excess sodium hydroxide and in, sorry, magnesium is the only one that is insoluble in excess sodium hydroxide and ammonia. To differentiate between lead and aluminum, you would use a solution containing iodide ions. The reason for that, lead ion will combine with iodide ion to give you a yellow precipitate. All right, let's put this into practice so we can get a better feel of the questions. If you are in here, I thought calcium was nice. Huh? Give me a second. So, but based on the book, calcium is not applicable to confirm whether the soluble are not in ammonia. Calcium is not soluble in calcium is soluble in ammonia. Is that what you're asking? Remember when you're doing qualitative analysis, you would not just use the ammonia solution only. So you start out with this sodium hydroxide, then you move to ammonia. So for calcium, you would have gotten a white precipitate that does not dissolve in excess sodium hydroxide. Remember, only 2 of these cations does not dissolve in excess ammonia. So before we move to the question, magnesium and calcium, they are insoluble in excess sodium hydroxide. We know that. But when you get to ammonia, calcium will not give you a precipitate with ammonia. So if after you use sodium hydroxide, you got 2 precipitates that were insoluble, right? Which would be calcium or magnesium. And when you get to ammonia, you don't get a precipitate. Then it means it will be calcium. And if you get a precipitate, then it would be magnesium. Just a second. Let's do this. Based on the concise book, calcium is blank and contains no precipitate in. Right. That is what I'm saying. You won't get a precipitate with calcium because calcium is soluble. So if it is, remember now, a precipitate means you are getting a solid being produced in the solution. So calcium, if you get a precipitate, then calcium is not present. But if you don't get one, then calcium is present. Now, if you're here, you should have gotten a PDF file with some questions. So we're going to start from the last question. So go to 2015. Give me a second. Hold on. So go to 2015. All right, so if you're asking which PDF, whoever sent you the link, just ask them to send you the PDF as well. Yes, I went through this sodium hydroxide about the sodium hydroxide ones already. All right, so we're going to work the questions now. So
Sir,
yes,
what were you saying about lead and aluminum for ammonia?
right. So so how this works, right? We normally start with sodium hydroxide and then move to ammonia. If you get a white precipitate, so for sodium hydroxide, if you get a white precipitate initially, and then when you add it in excess, it dissolves, that indicates three potential ions: lead, zinc, and aluminum. These three ions will dissolve in excess ammonia. Sorry, in excess sodium hydroxide, lead, zinc, and aluminum. Sorry, let me just add some. So if after you use sodium hydroxide, you figure out that it's either lead, zinc, or aluminum. When you get to ammonia, if you get a precipitate that is insoluble, so of those three ions, zinc, aluminum, and lead, zinc, aluminum, and lead, of those three, lead and aluminum are insoluble in excess ammonia. Zinc is not. So, right, so if you want to figure out if you have lead or aluminum, you're going to do a next test now. So ammonia cannot allow you to differentiate between lead and aluminum. What you are going to use is a solution with potassium that contains iodide ions. So you can use potassium iodide or sodium iodide. But any solution that contains iodide ions, you can use it, because what will happen, as shown here in the equation, lead ions will combine with the iodide ions to give you a yellow precipitate.
So one question. The mass, if you write the equation, so you can write it simple as that.
Yes,
Instead of
whenever
some
you
things say what I
have,
need for like write the potassium
no.
iodide and them something there.
So for qualitative analysis, you just need the ionic equation.
Oh.
Yeah. So lead ions combined with iodide ions to give you lead iodide. All right, so right, if you don't have the PDF, whoever sent you the link, just ask them to send you the PDF as well. All right, so remember, we're going to start from 2015, which is the last question in the PDF file. So it's 17 pages. So just scroll down to the final question.
So, excuse me, sir.
Yes.
So you say that PB 2+ and aluminum 3+ are insoluble in excess.
Ammonia, right?
So what about magnesium? Everything I need excess. You know, insoluble too, sir.
Yeah, man. No, but right. So let me just say it again. Remember, we use sodium hydroxide first, right? Then you use aqueous ammonia. So you remember, it's like you have a set of ions, right? A potential set of ions, and you have to figure out which one of them is present. So we start with sodium hydroxide first. Sodium hydroxide will give you an idea of which ion is present, right? Then you move to aqueous ammonia. That will narrow it down a little further. And then you use a solution with iodide to confirm it. So if you use sodium hydroxide, starting out with sodium hydroxide, this is how it will end. for sodium hydroxide. You're going to add it in excess. Two things will happen, one of two things, right? You will eventually add the sodium hydroxide solution in excess. The precipitate that was there, either it will dissolve or it will not. If you add the sodium hydroxide in excess and the precipitate dissolves, it's lead, zinc, or aluminum. All right? So let's pick up from there. If you add the sodium hydroxide in excess and the white precipitate that was formed dissolves, it can be lead, aluminum, or zinc. So we finish with sodium hydroxide now, and we move to ammonia. We are not focusing on calcium or magnesium. The reason for that, calcium, just a second, I soon type it. The reason I have not included calcium or magnesium is because calcium and magnesium, they are insoluble in excess sodium hydroxide. So they would have already separated themselves from aluminum, zinc, and lead. So if from you use sodium hydroxide, you know you may have aluminum, zinc, or lead. When you come to the excess ammonia now, we are trying to separate aluminum and lead from the zinc. So when you get to ammonia, if you get a white precipitate that is insoluble in excess ammonia, out of the three, so remember, aluminum, zinc, and lead. Of those three, zinc is soluble and aluminum and lead is insoluble. No. If you want to leave an email, I'm not sure, and I send it, I will send it.
I'm sorry.
Or you can text me on IG. I'm going to post my IG if you want to send your email there, and I can send it. All right. So whichever you want to do.
Sir,
Yes.
so Fe2 plus and them one is not really bad.
No, the reason why these are straightforward because Fe2 plus will give you a green color. So once you see a green color, that is Fe2 plus. Once you see a red-brown color, that's Fe3 plus. And once you see blue precipitate, that's Cu2 plus. So these are straightforward. But when you get the white precipitate, 1, 2, 3, 4,
Sir,
5,
what's your
7.
YouTube channel's name?
Just a sec, let me write it up here. It's Mr. Here's Chemistry Lecture Series. As soon as the class is finished, I will post the recording. All right, so these are straightforward. All right, let's work some questions so you can get a feel of it. All right, so let's go to the January 2015. Oh,
Yes.
remember qualitative analysis. It's for both positive ions and negative ions. So I've just shown you how to identify the positive ions. So we're going to focus on the questions that are dealing with the positive ions. Then afterwards, we will look at the ones dealing with the negative ions. All right, so let's scroll on to January 2015. Away from about this. All right, and with qualitative analysis, it's always a table where you will get test, observation, and inference.
Sir,
Yeah.
we're which people should I go to now?
Please repeat. Oh,
Which
so
people you are doing now?
well, 2015 January. All right, so for qualitative analysis, you will get a table, test, observation, and inference. All right, so it says to a portion, so under the test, to a portion of M, add aqueous sodium hydroxide until in excess. So we are going to add sodium hydroxide until in excess, right? And the inference, so we have 2 points. Where you see the 2 points, that means you must have 2 sets of observation. And they gave us 2 sets of inference. So the inference is, so the first inference is aluminum Al3 plus, Pb2 plus, Zn2 plus, and Ca2 plus possibly present. So remember now, we just did this, right? If you add the precipitate, so remember, we always add sodium hydroxide dropwise, then in excess. So the 2 points here, the first one is for when you add it dropwise, and then when you add it in excess. So if you add sodium hydroxide dropwise, and you get, and the inference is aluminum, lead, zinc, calcium possibly present, then what should be the observation?
White precipitate.
White is correct, right? I'm just going to put P for short. So white precipitate is formed, right? Now, for the second inference, it says aluminum, lead, or zinc possibly present. Right? Aluminum, zinc, or lead possibly present.
Sir,
Yes?
if we put, we can put soluble or insoluble.
Well, on the exam, they have that, but I was told that CSEC don't want us to use it anymore. So you should put that the precipitate dissolves. All right? So for your observation, put that a precipitate is formed, and then put that it dissolves. All right? So look at the inference. These possible ions were present. When you add it in excess, these 3 ions are possibly present. So based on what observation would they have made this hypothesis? Solubly in excess, right? So that means the precipitate would have dissolved. So the precipitate dissolve. All right? So the precipitate would dissolve in excess sodium hydroxide. That is how we would have known that it is either aluminum, lead, or zinc. Right? And that's your 2 marks. Good.
Sir, them would have go further, like them would have ask you sodium hydroxide, ammonium, and lead iodine, potassium iodide, all of them at once.
They can, but sometimes they mix it with both positive and negative ions. All right, so it all depends, but they could do it like that. All right, so that was the first column or the first row of the table, right? Now in the second portion, it says, for the second row, it says that to a second portion of M, at aqueous ammonia until in excess. So we are finished with the sodium hydroxide, and now we're moving on to ammonia. Before I move on to ammonia, look right here. We have moved from saying aluminum, lead, zinc, or calcium to saying that aluminum, lead, or zinc. So when we move to ammonia, the purpose of the ammonia now is to differentiate. The purpose of the ammonia is to differentiate between aluminum, lead, or zinc, because we have narrowed it down from aluminum, lead, zinc, and calcium to aluminum, lead, and zinc.
Sir,
Yes.
sir, for the one that for the observation that said the white precipitate form, magnesium could go there as well for the inference.
All right. It could, but because, just a second. So if it's insoluble in excess, right, magnesium could work. But remember, we are moving, you're working in a sequence, right? So when we're finished with the sodium hydroxide, there was here, remember we said the precipitate dissolves in excess sodium hydroxide. So the question is, would magnesium dissolve in excess sodium hydroxide?
No.
Exactly. So remember, the part you're looking at, it's still the same solid, right? M. It's still M we are working with. So if based on the reaction with sodium hydroxide, you know that magnesium is absent, then you wouldn't put it when you use aqueous ammonia. That is what I'm saying, it's a stepwise process. So if from here, magnesium was present, then you could have put that. But we have already said that M contains one of these three ions. So even though we know that magnesium is insoluble in excess ammonia, we already see based on this inference that magnesium is not present.
Okay.
You understand? Right. So it's based on what you do with sodium hydroxide. We are following it up now with ammonia to break it down even further. All right. So, so we switch now from sodium hydroxide.
Excuse me, sir.
Yes.
Sir.
Yes.
When you're going to do organism.
Is it repeat?
When you're going to do organism.
Organic chem?
Yeah.
Next
yes,
week.
Sir.
Yeah, I'm going to finish it up after this. As in, I'm doing qualitative and then I return to organic chem. All right. Sorry. Right. So for the observation, we get a word precipitate. Right. So once you get a word precipitate, what would be our inference?
So either magnesium, calcium, iron, or lead ions.
All right, so it could be, no, calcium would not be there. So remember, calcium is soluble in ammonia. So it would be zinc, aluminum, or lead. The reason, all right, even though magnesium, right, even though it is insoluble and will give you a precipitate with aqueous ammonia, you have to look at the question, right? Remember, in part one, the precipitate dissolves in, so remember, to a portion of M. In the second part here, it is still M. So in part one, when you add sodium hydroxide to M dissolves in excess sodium hydroxide. And we know that we know that magnesium is not soluble in excess sodium hydroxide. So in the first part of the experiment, we knew that magnesium could not be present in a solution of M. So if it is not present from part 1, you cannot put it for part 2 because we already eliminated magnesium from part 1. So it's not just putting any ion which may be insoluble. It's based on the context of the experiment. All right? So it's an actual experiment. And in part 1, we said that it was aluminum, lead, or zinc. So when you get a white precipitate, so your light is kind. I'm not sure why it does this with Zoom. When I use Google Meet, it doesn't do that. I'm not sure. Sorry about that. What's here? Right. So the precipitate is soluble in excess ammonia. So you get a white precipitate being formed. So we know it's zinc, aluminum, or lead. Then it says the precipitate is soluble in excess ammonia. Which of these 3 are soluble in ammonia?
Zinc.
Right. It's soluble. That means our inference would be zinc is present. Right. So of these 3, zinc is the one that is present. And also, right, we wouldn't get a white precipitate with calcium. So even though here it says the precipitate is soluble, we would not put calcium here, right? Because we already know that. So we should always put the ions. Yes. So zinc, right? Just list the ions. So for the inference, yeah, all you're doing is listing which ion may be present. Right?
Sir, could you
Yes.
repeat the points about magnesium that you were saying before, please?
Sure. All right, so we know that magnesium is insoluble in ammonia and calcium is soluble, right? However, when you get the test right, you have to look at what we start with. So in the first part, in test 1, we were using sodium hydroxide. And the inference tells us that aluminum, lead, or zinc is possibly present. So once we finished with sodium hydroxide, we had drawn a conclusion that calcium or magnesium was not present. So once you make that conclusion with sodium hydroxide, you cannot follow up now and then say that calcium or magnesium is present when you use ammonia, because you already figured out that it was absent when you use the sodium hydroxide.
Okay, thank you, sir.
Yeah. So even though we know that it is insoluble based on what we're, sorry. Right, even though we know that magnesium is insoluble, we cannot put it here based on the fact that when we use sodium hydroxide, we saw that it was not present. That means magnesium is not a part of the compound M. All right. So that is the 2 marks here. For the first part, jump-wise, and in a white precipitate, those 3 may be present. The precipitate is soluble. That means zinc is present. All right. In the next part of the question, it says to a third portion of M, add aqueous sodium iodide. And the observation was that we get a yellow precipitate. All right. So if we add sodium iodide, once you hear iodide, which ion are we testing for? Which positive ion?
Lead, sir.
Lead. All right. And the observation is that a yellow precipitate is formed. So once you get a yellow precipitate, which ion does a yellow precipitate come from?
PB2 plus.
PB2 plus, that's correct. So PB2 plus is present, right? And that's 1 mark. They could have asked you for a balance equation, all right? If they asked you for an equation, it would be, as I said before, PB2 plus 2I minus to produce PBI2. Right?
So our balance equation for ammonia would look.
Again, so aqueous, when we say aqueous ammonia, it's actually, so when you dissolve
Is
ammonia.
the hydroxide, ammonia hydroxide?
Yes, that is what I was getting to. So aqueous ammonia is ammonium hydroxide. So it's just like reacting. So it's the positive ion with the hydroxide ion again. So aqueous ammonia. So NH3 aqueous is actually NH4OH. They're the same thing, all right? Aqueous ammonia is ammonium hydroxide. So what is taking place would be the positive ion with the hydroxide ion. That is the reaction that is taking place, all right? So ammonium hydroxide and aqueous ammonia, they're the same compounds because aqueous ammonia means you dissolve ammonia in water, all right? In which case you would get the ammonium hydroxide. Now the last part of the question, that's negative ions, and we don't do that as yet. All right, so scroll up to the next page now in the same document. So that would be 2013. So we finish with January 2015.
Can I excuse so I can see the board quick?
Please repeat.
Can I excuse so I can see the board quick?
Oh, sure. Yeah, man.
Thank you, sir.
Yeah, man. All right, so let's scroll up to 2013.
Sir.
Yeah. Go ahead with your question. Right, so I'm going to erase the board now and we'll look at 2013. Is anybody writing? Before I finish the erase? All right. Just a second. Right, so in 2013, this one, it was a simple, this one was a simple one. All right, so part one, we're not doing part one. I haven't explained part one to you as yet. So we're going to do the second part where it says a solution of potassium iodide was added to a solution of Q. So again, once you see potassium iodide, we are testing, that is correct. We are testing for lead ion. So again, the test here, they were using potassium iodide. And they gave us the observation that we get a bright yellow precipitate. All right? And our job now, so for the inference,
PB2 plus.
is it
PB2 plus.
That is correct. PB2 plus is present. But they gave us 2 points, all right? If you notice here, it says balanced ionic equation required. So you put your PB 2 plus is present, and then write the balanced ionic equation. Include your state symbols as well. Right. And so that was the only one from 2030. All right, so here's the basic gist of it. This is how it will look, right? Sir, I'm not seeing the question, but it's right above the one from 2015. Says the second to last page. So 2013 is the second to last page in the document. All right, so let me introduce you now to the negative ions quickly, and then we'll see if we can work some more. All right, so let's do the negative ions. So the anions, so the anions that you will have to know, you will have to know the halide ions. Halide means halogen, which is group 7. So you will need to know the chloride ion, bromide ion, and iodide ion. All right. For this ion, we are going to use, so the reagent that we're looking for, so again, with these ions, the reagent is the clue. So when you're testing for these ions, when you see the name of the reagent, that will tell you which negative ion you are testing for. So once you see nitric acid, should have just write the formula. Once you see nitric acid and silver nitrate, you are testing for the halide ions. Right. Also, ammonia solution. All right. So nitric acid, silver nitrate, and aqueous ammonia. These are the reagents that you look out for when you're testing for the halide ions. All right. What will be your observation? For the chloride ion, you will get a white precipitate that dissolves in dilute ammonia solution. For the bromide ion, you will get a cream precipitate. All right. And it dissolves in concentrated ammonia. And for the iodide ion, you will get a yellow precipitate. And it does not dissolve. So let's just put insoluble. So the chloride ion, you will get a white precipitate that dissolves in aqueous ammonia. Bromide, cream precipitate, dissolved in concentrated ammonia. And iodide ion, you will get the yellow precipitate insoluble in ammonia. All right, when you finish with this, you'll let me know again. All right.
Sir,
Yes.
Yes, sir.
the inference we have, sir, that when it react with what? The inference you have for all of them. Like for the chloride, that when it react with the ammonia.
Oh, so the color is for the silver nitrate. Yeah, thank you for that point. So the color is for the reaction with silver nitrate. All right, so they can just give you for silver nitrate. So it's the name, just a second. Silver nitrate followed by aqueous ammonia. Just a second, let me just check something here on the text. Silver nitrate followed by aqueous ammonia. That is correct. If it's the same structure. So for the halide ions, what you will, so what will be stated in the method, you add nitric acid and silver nitrate, right? If that is just what you see, you will just put white precipitate. For the observation, it will either be white precipitate, cream precipitate, or yellow precipitate. So if there's no mention of ammonia, you don't need to mention about anything dissolving. So the nitric acid, so typically we just use nitric acid and silver nitrate and done, right? But you can go a further step and add the aqueous ammonia. So once you see aqueous ammonia, then you will add in the part about dissolving, right? But the colors are for the silver nitrate. And the equation for the halide ion, this one will require or may require an equation. So they can ask you for it. So the reason when you add silver nitrate to your halide ion, the reason why you get a precipitate is because silver ions, so Ag plus, that's this silver ion, it will combine with any of your halide ions. If you remember, in grade 10, when I did acid, bases, and salts, and I learned the solubility rules, we know that the salts of the chloride of the halide ions are soluble, except for one ion silver, as well as lead. So silver ion will combine with lead ion, silver ion will combine with your halide ion to form silver chloride, which is a solid, right? So that is how you get the, so you will get a white precipitate of silver chloride, a cream precipitate of silver bromide, yellow precipitate of silver iodide. So this is the ionic equation. Silver ion with any of your halide ions, all right, to give the silver halide, whether silver chloride, bromide, or iodide. So if you're asked for an equation, this is the equation. Silver ion plus the halide ion, right, to give you the silver salt.
So why the normal put the nitric acid first?
So the nitric acid is to remove any impurity from the container or from the solution.
Okay.
Yeah. So you just want the silver ion to be reacting with the halide ion. Ready again?
Yes, sir.
This is the answer for the last one. Last one for the 2015, right?
Right. What was the observation again for 2015? Or the test? What did it ask?
The observation said no observable change.
Right. That means no halide ion was present. So probably sulfate or nitrate was present. Right. So so once I say silver nitrate, that is why I said for the negative ions, the reagent is the ink. So once I say silver nitrate, you know that you're testing for the halide ion. So if you don't get any form of precipitate, no halide ion is present. All right, the next.
What is the answer for it, sir?
No halide ion is present.
Sir,
Yes.
repeat why you say no halide ion is present.
All right, so in the test, they use silver nitrate, right? And we know that once you see silver nitrate, you're testing for the halide ion. But if it was present, you would either see a white precipitate, which would mean chloride is present, a cream precipitate, which would mean bromide ion, or a yellow precipitate, which would mean iodide ion. But in the observation on the paper, they said there were no observable changes, right? So if you use silver nitrate and you don't get a reaction, that means there are no halide ion present in this solution, all right? Understand?
Yes, sir.
All right. So the next negative ion we're going to look at.
So she said no halide ion present.
Present, right.
Okay.
And you can put possibly nitrate ion or sulfate ion. So nitrate, sulfate, or sulfate. So no halide ion is present. So it's possibly that one of these ions are present. Because if halide ion is present, please repeat.
Repeat that, sir.
Right, so no, once you don't see a reaction, no halide ion would have been present. The nitric acid would have gotten rid of the CO3. So the possibilities would have been one of these ions. All right. And we're going to look at how to test for each of these ions, nitrate, sulfate, and sulfide, as well as carbonate. All right, so let's start with the nitrate. Now, first, we're going to look at what happens if you heat a solid nitrate compound. So first, if you heat it, and you get a reddish brown gas. All right, and it's acidic, so reddish brown, reddish brown gas that changes blue litmus to red. That gas is NO2, nitrogen dioxide. So in qualitative analysis, we use the presence or the formation of a gas to indicate the negative ion that is present. So the nitrogen dioxide would be coming from the decomposition of the nitrate salt. Just like when we say carbonates, they will decompose to give you the oxide, the metal oxide, as well as carbon dioxide. So
this is nitrogen dioxide.
Right. So when you heat your nitrate, nitrogen dioxide would evolve. It is an acidic gas. That means if you were testing it, it would turn damp blue litmus to red. Because remember, acids change blue litmus paper to red. So that is what would have happened. All right. So other than heating the compound now, if we actually have a solution, so this is if you are heating this solid. So for this one, you heat the solid compound. If you have the solution now of the nitrate, if you have the solution, just a second. If you have a solution of the nitrate, again, the reagents are the clue. This is sodium hydroxide and aluminum powder, or any form of aluminum metal. So aluminum foil, possibly. All right, so
Sir, what did you say about the solution?
So, right, so there are two ways, or more than one way the question can come. So you can heat this solid, right? And if you get the brown gas, that's NO2. But if you have a solution of the nitrate, what we would do is add sodium hydroxide solution and aluminum powder, then we heat it. So it's sodium hydroxide solution. So let me put aqueous. So it's sodium hydroxide. The solution here is a solution of the nitrate. So solution of the nitrate. All right. Jeez, let me just look. Right, so if you are testing for this solution of the nitrate, you can use sodium hydroxide solution and aluminum powder. Then you heat it. Now, when you heat this solution, you will get ammonia gas. So on the paper, what you're looking for, the reagents are your hints. If you see sodium hydroxide and aluminum powder, right? So if you add sodium hydroxide and aluminum powder to the solution and you heat it, a gas will evolve, right? Ammonia gas is given off. So just remember, once you see sodium hydroxide and once you see sodium hydroxide and aluminum powder, that's for ammonia gas. And they are testing for the nitrate ion. Good. What is going to happen? To confirm the ammonia gas, is it acidic or basic? Anybody know?
Basic.
Basic.
If it's basic, which color litmus paper would we use?
Blue to red.
Right. So would you no the other way?
Red to blue, yeah, red to
Right,
blue.
because it is basic, right? So when you use the sodium hydroxide and the aluminum powder, ammonia gas is going to be given off. And you would place a piece of dumb red litmus paper at the mouth of the container, so the fumes would change it from red to blue. So, as a side note, it will change red litmus to blue.
So, sir,
Yes.
ammonia turns moist red litmus paper to blue.
Yes, let me put in the moist. Yes, we have two moist. So let me just. So it changes moist red litmus to blue.
Sir,
Yes,
why is it moist red litmus paper?
because it's a gas that is being given off. So if you use a dry piece, you won't get the color change. You have to dampen it with some water. Because remember, we normally put the paper in a solution, right? So we dampen it with some water, then we place it over the mouth of the test tube. All right?
Yes, sir.
No, typically,
Sir,
we don't, yes, go ahead. Someone is asking a question? All right, so I would say normally, or the most times we would use sodium hydroxide and aluminum, right? But according to the paper, I think it was 2010, they used copper and sulfuric acid. So I'm just going to add that here as well. But normally, what we use is sodium hydroxide and aluminum. But I saw copper and sulfuric acid, so I'm just informing you of that one as well.
Sir, so what you're saying is that for since you said it was solid, it turn reddish brown gas. It will produce reddish brown gas and change litmus paper to red, and it also produce
All right, so just a second. So the nitrate, right? Remember, it's going to be an ionic compound. So you have the positive ion and the negative ion. So you have the crystal, right? Because it's a salt. So you can heat the solid form of the salt, right? So if you heat it, it is going to decompose and give you a gas. The gas that evolves, it is nitrogen dioxide and it is a brown gas. It is acidic. So reddish brown gas, it is acidic. All right. And so because it is acidic, it can change the blue litmus paper to red. So ammonia is a basic gas, but NO2 is an acidic gas. So for NO2, it changes blue litmus to red, but for ammonia, it will change red litmus to blue.
yeah, it would also produce ammonia.
Not the solid form.
No,
the
in
solution.
the solution form.
Right, yes. So when it is the solution, you get ammonia gas. But when you eat the solid, you get NO2. You actually get two gases. It's not only NO2, you also get oxygen, right? So you get, when you heat this solid, you don't just get NO2, you also get oxygen, right? So let me just add that. Right, so when you heat it, you get NO2 and oxygen, all right? But it is the NO2 that is confirming the presence of the nitrate, right? And so remember now, most times, most of them is aluminum and sodium hydroxide. As I said on the 2010 paper, I think it was, they use copper metal, and sulfuric acid. But in terms of observation, it is the same thing. You will get the ammonia gas, and you test it using red litmus paper. So if you see copper and sulfuric acid, it is still ammonia gas that is being tested for. But more than likely, we will see sodium hydroxide and aluminum, because that is what we normally use. Sodium hydroxide and aluminum. All right. If you happen to see copper and sulfuric acid, it is still aluminum.
Nitrogen dioxide and oxygen.
Right. So when nitrates decompose, you get nitrogen dioxide and oxygen. But it is the nitrogen dioxide that is of importance.
Okay.
Yeah. All right, so after this, we are going to look at this sulfate ion. Is anybody writing? Or finish?
Soon, sir.
All right.
Wait.
I'm sorry. It was, what was there? So we add NO2 here. Right? So when you heat this solid, you get NO2 and O2.
Sir, put back in NO3, sir.
All right.
Yes, sir, I got it now.
All right. Anybody else before I erase?
Finish, sir.
All right.
I have a question.
Sure.
Sir, does NH4 NH3 also turn blue litmus paper red?
No.
Okay.
It is basic. So remember, bases change red litmus to blue, and acids change blue litmus to red. So because it's a basic gas, it will change red litmus to blue. All right, so for this sulfate ion, sulfate, all right, you will use hydrochloric acid and barium chloride, all right? Most cases, you will see barium chloride, but you can also use barium nitrate. All right. Again, just like with the nitric acid, the hydrochloric acid is to, in this case, is to remove any impurities. Specifically, I'm talking about the carbonate ion here.
So you can use any acid as a, you have to use a specific acid for the test.
For this one, it was hydrochloric. But for sulfuric, because you are testing for sulfate,
Yeah.
you don't want, remember, sulfuric acid contains sulfate ions, right?
Yeah.
Right. So you don't want to use the sulfuric acid here.
Yeah.
What is, for this one, it's a straightforward reaction, right? Again, it comes back to the solubility rules. If sulfate is present, the barium ion. So let me just explain this quickly. If we say we have a solution of barium chloride or a solution of any compound, right? Once you have a solution of a compound, even though we break the compound, right, as BaCl2, in reality, what you have is barium ions and chloride ions in this solution. So when you add a solution of barium chloride, the barium ion, just a second, let me mute somebody mic is on. Right. So when you add a solution of barium chloride, the barium ions are going to combine with the sulfate ions. So you get barium sulfate. So the barium ions are going to combine with the sulfate ions, and you get barium sulfate, which is a white solid. So again, the reagent is the hint. Once you hear barium chloride, you are testing for sulfate ion, right? Barium chloride or barium nitrate. Once you hear silver nitrate, you are testing for the halide ions. Barium chloride, you are testing for the nitrate ions. Ready again?
Sir?
Yes.
Sir, this is for the second part.
In terms of
the paper 2013.
Oh yes, so remember qualitative analysis, it has positive ions and negative ions. So I showed you the positive ions first. So now I'm going through the negative ions that you must know so that you can work the rest of the questions. So you must know sulfate. After sulfate, you must know how to identify sulfite. So with the sulfite, you are going to heat the solution . You're going to heat this solution with sulfuric acid. You will get a gas, which is SO2. So sulfur dioxide will be produced. Sulfur dioxide is an acidic gas. So after sulfate, sulfite. Now, since this is an acidic gas, right? Normally, we would use litmus paper for this one, right? We can confirm it. What they use for this one to confirm it is potassium permanganate or potassium dichromate. Now, if you are using KMnO4, it will change from purple to colorless. So if you are doing qualitative analysis, just a second, let me add someone. If you are doing qualitative analysis and you see KMnO4 and you see KMnO4, change the only reaction that we are going to use potassium permanganate for is sulfite. And it is to confirm, remember, we would heat this solution with sulfuric acid and we would get our acidic gas, which is SO2. We can bubble the gas in potassium permanganate. Right, we're testing for sulfite, but what we're using to, so even though we're testing for sulfite, each of these negative ions can produce a gas. So if we confirm the presence of the gas, then we can confirm the presence of the negative ion. So like the carbonate ion, that can produce carbon dioxide, and we can confirm CO2. The nitrate ion, it can produce ammonia or NO2, which we can confirm. So when you confirm the gas, we also confirm the ion. All right. For this one, once you see KMnO4, it's the only ion that we are going to use KMnO4 for. So once you see KMnO4, we are testing for this sulfite ion. Go ahead.
Sir,
yeah.
Is which question? Are we at a question still?
No. We are not working questions.
Okay.
Right. I am showing you how to identify the negative ions.
Sir.
So just like how we showed you how to identify the positive ones, you have to know how to identify the negative ones, specific negative ones. Right. So this syllabus gives us the specific ions that you should know. All right. So for the sulfite ion, you will heat the solution with sulfuric acid. It will produce sulfur dioxide, which is an acidic gas. How do we test for sulfur dioxide? You can use a solution of potassium permanganate. The potassium permanganate will change from purple to colorless. If you use potassium dichromate, K2Cr2O7, it will change from orange to green. Right. So if you see any of these oxidizing agents, we are confirming the presence of sulfur dioxide, right? Which will confirm that if or not, sulfite ion is present, all right? So these are the reagents we use to confirm the gas. It's an acidic gas, that means blue litmus. Will change to red. But more than likely, if this question comes, you will get either KMnO4 or dichromate. Next thing I'm to point out, SO2 is a colorless gas. And they describe it as having a choking smell. So for sulfide, the first thing, heat this solution with sulfuric acid. You will get a gas. What will we do with the gas? We will bubble it through a solution of potassium permanganate. If you change on purple to colorless, then we know SO2 was given off. For the dichromate, we will actually get like a piece of filter paper and dip it in the solution of potassium permanganate, and then allow the gas to pass over it. So this is for the sulfide ion.
Sir,
Yeah.
when the potassium permanganate change color, that means it reduce.
That is correct, right? Yeah. Because remember, it's an oxidizing agent. So if it reacts, it is going to be reduced.
Sir.
Yeah.
When you say your bubble, what should I guess? Let me say a bubble with.
Oh, yeah. So we would pass the gas through potassium permanganate, the SO2. So we'd have to set it up so that when the gas is produced, it will go into a solution of the KMnO4. So if it changes from purple to colorless, when that happens, then we know that we have SO2 for sure. All right, after this, we're going to do the carbonate ion and the ammonium ion. So I forgot to do the ammonium ion, which is a positive ion. So we just have two more ions, the carbonate ion and the ammonium ion. So as soon as you have finished, you can, could you repeat what you said about SO2 being present? All right. So if you get a question, right, and you have this solution of your negative ion, if you see they heat this solution with sulfuric acid, and they will give you stuff, right? So if a gas is produced, right, and that gas, they can say it is a colorless gas with a choking smell, right? They will tell you some stuff. Or the gas produced, it changes potassium permanganate from purple to colorless. You have to look at all the info. So for sulfuric ion, you look for heating this solution with sulfuric acid. But that's not the only thing that they will tell you. They will have to give you some more of these information. So after you heat it, the gas produced does something. That is how it will go. So you heat this solution with sulfuric acid, right? A gas is produced. The gas that is produced must do one of these. That is how you will know it is SO2. All right?
Sir.
Yes.
So mostly gas we produce, we go focus on.
Right, because it is the gas that is produced that is going to allow us to know which ion is present. Because remember, the nitrate ion cannot give you sulfur dioxide, and the sulfide ion cannot give you ammonia. So, and likewise, the sulfide ion cannot produce carbon dioxide. So if we confirm the presence of the gas, each negative ion produce a particular gas, right? Well, for this sulfate, we're not getting any gas with that, right? Because we react it with barium chloride and we get a precipitate of barium sulfate. But for the carbonate, the nitrate, carbonate nitrate, and sulfite, These three produce a gas. And those gases is what we use to confirm the presence of each of those ions. So we use ammonia to confirm nitrate, carbon dioxide to confirm the carbonate ion, and we use sulfur dioxide to confirm sulfide. We also use nitrogen dioxide to confirm nitrate. Go ahead now. The person that was asking.
Sir, it's a choking smell. The adjective they say, what do you mean by that? You're a choking smell.
It's from the literature again. That's how they describe it. It has a choking smell.
So for example, sir, they say you smell the gas, right? Yeah, could you start choke or something?
Yes. Well, that is what I would presume from it. If it has a choking effect. I don't know why they say choking smell, but it will have a choking effect.
It's strong.
Right.
It has a strong odor.
Right. You can put for ammonia, you can put pungent. So ammonia, in terms of scent, ammonia is a pungent smell. So if they say a pungent gas, that would be referring to ammonia. So you can make a note of that as well. In terms of the scent, ammonia, it has a pungent smell. All right. The carbonate ion, it's kind of simple. All right. Is anybody writing? Are we good? We good now? We can move to carbonate.
Yes, sir.
All right. So if you heat this solid carbonate, right, which gas is produced?
Sir, repeat.
When you heat a solid carbonate, which gas is produced? Like for instance, if you heat calcium carbonate and it decomposes, right, we will get carbon dioxide. So if you are testing for the carbonate ion, you can heat this solid, right? When you heat this solid, CO2 will be produced. How do we confirm CO2? CO2 turns lime water. Now, when you get the question, once you see lime water, let me highlight it. Once you see lime water, we are testing for CO2. Right? So carbon dioxide will turn lime water, which is calcium hydroxide, which probably should use a bracket here, and CaOH2. All right, so lime water is calcium hydroxide. Let me just use a bigger bracket. So it will turn lime water milky. So once you see this observation turns lime water milky, we are testing for carbon dioxide. We are confirming that carbon dioxide is present. All right. So that is if you have the solid. Now, if you have a solution, question, when carbonates react with acid, what is produced? Anybody? So like if you react a solution of sodium carbonate with hydrochloric acid, you will get three things.
Is it salt, water, and carbonate?
Carbon dioxide.
Carbon.
Right. So if you have this solution and you react it with acid, that means we are going to get CO2.
Salt, water, carbon dioxide gas.
Right. So for the carbonate, if you heat this solid, it will produce CO2. So you just need to pass the gas. You just need to do a setup where the gas is allowed to flow into a solution of lime water and it will turn milky. This reaction is on the channel as well if you want to see. So what I did, so you have two test tubes, right? And you have the acid and the carbonate in this one. So when it reacts, it is going to produce carbon dioxide. But the carbon dioxide is not allowed to escape. All right. So I placed a tube in both of the test tubes. This one, it has in calcium hydroxide, which is the lime water. All right. So what happens when the acid and the carbonate is in this test tube and it reacts, the carbon dioxide that is produced, it goes into the tube, right, and comes down into the solution of calcium hydroxide, which is when it gets milky or white. All right. If you get a white, so for this, if they say you get a white precipitate with calcium hydroxide, it is still CO2. So anything to do with lime water, it's CO2. So even if they don't say turn lime water milky, if they say you get a white precipitate with calcium hydroxide, aka lime water, you are still testing for CO2. Once you say lime water and you get something white, calcium hydroxide, sorry, CO2 is present. All right. So all we are doing is either heating the carbonate to give off CO2, or we are reacting a solution of the carbonate with CO2 to, sorry, a solution of the carbonate with acid, and again it will produce CO2. So how we know the carbonate is present is by confirming the presence of CO2, because the only negative ion that is going to produce carbon dioxide is the carbonate, all right? Not the nitrate, not the sulfate, not the sulfide. So if you confirm carbon dioxide is present, then it means that the carbonate ion was there all along. All right. So right. So this one is kind of easy. And then once you're finished with that one, the last one leave is ammonia, which is also a straightforward one. So as soon as they're finished with this one, they can let me know. Third most go. No, CO2 is a neutral. No, it's yeah, this is an acidic oxide. But we don't normally use litmus paper. We use lime water. Right, is anybody writing still from the board?
Yes, sir. Finish.
All right.
Wait, sir. Somebody said no.
So all we did was, if you have this solution, you add acid, any acid to the solution, and CO2 will be produced.
Oh, sir. Wait, the person that they're not writing, so you can erase it.
All right. Thomas. All right, so for the ammonium ion, if you want to test it, you just add sodium hydroxide solution and heat. So all you're doing is add the sodium hydroxide solution and heat it. You will get ammonia gas. All right? So you add this sodium hydroxide and heat it, ammonia gas will be given off. How do we confirm ammonia, or how do we test for ammonia? Anybody? How would we test for the ammonia form?
So litmus paper.
Right. So we know that ammonia the ammonium will turn down. Ammonia will turn down red litmus blue. All right. So the negative ions we need to know are the halide ions, carbonate, sulfate, sulfite, and nitrate. All right, to finish off, I'm just going to remind you how to test for hydrogen
So
gas.
the ammonia we just do is for the hold on.
Ammonium ion. But in any, it doesn't matter which reaction the ammonia gas is produced, you will confirm it this same way with the damp red litmus paper. But remember, the reagent is what is giving you the hint. Because if you see our iodine, sodium hydroxide, and heat, that is only for the ammonium ion. Does anybody know how we test for oxygen and hydrogen? So those are the two gases that we need to remember. How do we test for oxygen and hydrogen?
With splint? The splint?
series of glowing splint.
Somebody said glowing splint. Which one is the glowing splint?
Oxygen, sir.
Right. And what will happen to the glowing splint?
Like a relight.
Right. So for oxygen gas, it relights glowing splint. What about hydrogen?
Out it.
With what kind of tone? Right.
Pop song, sir.
Pop song.
Right. No, for hydrogen, it's not a glowing splint. It's actually, so when you say glowing splint, it means you light it, but there's no flame on it. But with the hydrogen, it will out.
A lit splint.
Right. With a pop song. And so that is it for qualitative analysis. You just need to remember all of these. So it's now 8:30. Let us just look back at the two tables we did. And the next class, we will do some more and continue organic chemistry.
So when is the next class? Next week?
Right. So, all right, so this, right, so back to 2015. Right, so we had answered it already, but let's just do it again. So it had said to a fourth portion of M at aqueous silver nitrate followed by aqueous ammonia. Once we hear silver nitrate, which negative ion are we testing for? Once we hear silver nitrate.
Halide.
Halide, good. Now in the observation, let's say chloride ion was present. What would have been your observation?
White color.
Yes, right, a white precipitate. Yes, it will be the same link. All right, if you had see if it was bromide ion, what would have been your inference?
Green precipitate.
Right, and if it was iodide, it would have been yellow. If you were asked to write an equation for the inference, let's say chloride ion was present, and you were to write an equation, what would the equation be?
Silver chloride.
So, right.
Silver plus
ion.
silver
Right.
ion plus the chloride ion.
Silver ion plus
Chloride
ion
equals silver chloride.
That is correct. Now remember to put your state symbol. Once it has a charge, it's aqueous.
Solid.
it is insoluble, right? So it is a solid. Right. Now the next table, 2013. So for 2013, right, so the PDF file, I just cut qualitative analysis from a couple years and put it in one PDF file. All right, so just scroll up to 2013 now. In the first test, it says a small amount of solid Q was placed in a test tube and heated over a Bunsen burner flame. A brown gas was produced.
Nitrogen dioxide.
Right. Did I tell you the color of NO2? Oh, yes, I did. Right. So remember, when you heat a nitrate, you get a brown gas, right? So it was NO2. We know that. And it also said that it turns blue litmus red, which means that it is acidic, right? No, you wouldn't put oxygen, right? You would just work with NO2, right? So a brown
That
gas,
have been nitrogen dioxide.
that is correct. So a brown gas was produced. We say nitrogen dioxide is present. The dark blue litmus to red. The NO2 would confirm the presence of the nitrate ion. So it also put that the nitrate ion is present. All right. So once we know which gas is present, we also know the ion that is present. So if nitrogen dioxide is produced, it means that the nitrate ion is present. And that's how we would answer that one. All right, let's just do the final one, 2012. All right, let's just do the 2012 table and finish out. All right, so the first test, we add aqueous sodium hydroxide gradually until in excess. You get a red-brown precipitate. Which ion is red-brown? Which positive ion? As a
Fe2 plus.
Fe3. Right, that's correct. So for the inference, we know that Fe3 plus is present. That is why I say that the colored ions are straightforward. So when you get a blue precipitate, wait, when I was doing copper, I said that copper gave you a white precipitate, that copper 2 was insoluble in excess ammonia. No, it's not. It will dissolve to give you a deep blue solution. So Cu2 plus, just remember I didn't point that out. So Cu2 plus, so you would get a blue precipitate, right? But it dissolves in excess ammonia to give a deep blue solution. All right, so copper 2 plus, it dissolves in excess ammonia. Yes.
So, sir.
Yes.
Sir, it does not dissolve in sodium hydroxide?
No.
Okay.
All right. All right. So the second part now, test 2, it says a strip of magnesium ribbon is added. And below that, aqueous sodium hydroxide is added to the mixture until in excess. When you get a question, just pay attention to everything that you're given. So they said that a strip of magnesium ribbon is added. If you look across, the observation is empty. At that point, let's go to the inference. For the inference, it says the magnesium reduces solution Y. Iron 2 ions are present. So let me tell you what they're saying there. So we have magnesium with a solution of Y, right? And for the inference, it says magnesium reduces solution Y, and we get Fe2 plus ions. So if magnesium, so whichever ion was in solution Y, it was reduced to Fe2 plus. So if you get Fe2 plus, which ion do you think?
SO4 sulfate.
Wait, hold on. It was reduced to Fe2 plus. So which ion do you think would have been reduced to Fe2 plus? Powell,
E3 plus.
right. It will have to be Fe3 plus. Right. So magnesium, if you are getting Fe2 plus, and it was formed from something that was reduced, Fe2 plus could only be coming from Fe3 plus.
So I thought it was like a displacement reaction or something like that.
It is a displacement, right? Because the magnesium would be displacing the Fe3 plus, right? Yeah. But remember that if you get Fe,
it reduces, you get a, yeah, I understand.
Right. Let me quickly pick up a question. All right. So we still haven't started answering it yet. No, we're just looking at the hints. So all right. So now, if you know that Fe2 plus was produced, what would have been our observation? So we know that iron 3, what is the color of iron 3?
Reddish brown.
Red brown.
So iron 3 is red brown. All right, and it's a solution. So we have a red brown solution. Now, if you have a solution of iron 2, what would have been in the color?
Green.
Right. So we would have gotten a green solution. So in terms of observation, right? What would have been the color of this solution? It would have been red brown. This would have been reduced to Fe2 plus. That means the solution would have changed from what? Red brown to
green.
Green. Because when a redox reaction is taking place, you are going to have a color change. These are transition metals. So when they change their oxidation state, they change color as well. So when Fe3 plus becomes Fe2 plus, the entire solution is going to contain Fe2 plus ions. So the solution, the color will change from red-brown to green. Now in the observation, there are 2 points. So you must make 2 observations. So the solution changed from red-brown to green. Now, if it's a displacement reaction, and the magnesium displaces the iron. This iron is going to Fe2 plus. What is happening to the magnesium? Because you place a piece of magnesium in it, right? What is going to happen to will it stay as the piece of magnesium metal?
Not that would dissolve.
Exactly right. So the magnesium metal. So the first point we could make for the color change and then tell also what happened to the magnesium metal. So the magnesium ribbon dissolves in solution. So when you look at this solution and see the magnesium ribbon dissolving, it's actually the reaction now, the redox reaction that is taking place between the magnesium and the Fe3 plus ion in solution. All right. Now, so that was the 2 observations that we should put in that column. And to prove our point about the green solution, if you look now at the test again, it says what? Aqueous sodium hydroxide is added to the mixture until in excess. And it says that green gelatinous precipitate insoluble in excess sodium hydroxide is formed. So the solution was a green solution. And so when you add the sodium hydroxide, we expect to get a green precipitate because we know that Fe2 plus is insoluble in sodium hydroxide. Right, so that is in there, right? And they asked for a balanced equation. So since we did this at the start of the class, who can tell me the balanced equation for that reaction?
So the iron 2 plus and the hydroxide ion.
So Fe2 plus
Fe2 plus.
of the hydroxide ion
Two.
to produce
Iron hydroxide, Fe2 plus hydroxide. O2.
OH bracket 2.
OH2, sorry.
All right, don't leave off the state symbols.
And 2 right to the OH, sir.
Yes, thank you for that. All right. So that's our equation. And then dilute, all right, so test 3 now, we see what? Dilute nitric acid followed by barium nitrate. Once you say barium nitrate, which ion are we testing for?
Sulfate.
Sulfate, that is correct. Now, if sulfate was present, what should have been our observation? If sulfate was present, what would have been our observation?
White precipitate.
White precipitate, that is correct. But since as no precipitate is formed, is this sulfate ion present?
No,
No,
No, sir.
Right. So the sulfate or inferent sulfate ion is not present. All right.
Right, sir.
The fact that we see barium nitrate, it means that we are testing for sulfate ion. But because no precipitate was formed, it means that no sulfate ion is present. Because if sulfate ion was present, we would have gotten a white precipitate. And so now for the final one, test 4, it says silver nitrate. And once we hear silver nitrate, which negative ion are we testing for?
Halide.
Halide. Good. So we add silver nitrate followed by aqueous ammonia. And for the inference, what does it say? Chloride ions are confirmed. So silver nitrate, so remember now, silver nitrate is going to give you one observation and aqueous ammonia is supposed to give you a next one. So what are the 2 observations? White precipitate is formed, that is correct.
White precipitate and when dissolve.
Right, that is correct. So a white precipitate form that dissolves in the ammonia. Wonderful job. The person that wanted me to email the PDF, can you send back an email? All right, because I'm going to, sorry. All right, so I'm going to stop the recording here and we're going to close for tonight.